Alright, so welcome back for today. I want to talk about writing half reactions. Half reactions are really important to the in-between of understanding what's going on and the transition from talking about redox and kind of this, okay, well this is oxidation, this is reduction way, into what can we actually do with this in a lab. And I'm going to try to do a couple of demonstrations as part of this reaction actually, so hopefully we can get there through this. Our main goals today are to actually be able to do what this card says, to write a half reaction. And that's a little new to us, so we'll kind of take it slowly. Right off the bat, let's do a quick warm-up question. In a second, Edpuzzle is going to ask you which of these two things is, let's go with the oxidation. So which of these two things is being oxidized, that is losing electrons? Alright, so calcium is oxidized. That's because the number went up, right? Because this number went from 0 to 2, got bigger, it had to be oxidized. And the reduction reaction here, because the number went down, 0 to -2, is the oxygen. So knowing what lost and gained electrons is really, really important. And hopefully the homework assignment you did before helps you understand this. And at this point, this feels pretty much like, yeah, I got it. If you're still stuck, it'd be good to either go back and watch the last video, do a couple quick homework questions over, or email me or ask a friend, you know, the normal game. Because at this point, I'm going to use these terms like you understand it, that the number going up is oxidation and reduction is going down. So, this is the big picture right now, that if we lose electrons, we're being oxidized, right? But this actually is all there is to half reactions as well. Kind of keeping this off to the corner for the moment lets us deal with things here in a bit. In the meantime, I kind of did you a disservice, although on purpose, to be clear, and I didn't tell you what a spectator is. And they showed up in the last couple homework problems, and I'm assuming they didn't cause you too much problem. A spectator is a chemical which does not change its oxidation number, its green number, in the reaction. So spectators are just things that watch the other reaction happen. Kind of like in a precipitation double displacement, they're the ions that are present in the same before and after. And spectators are really common in redox as well. And in a redox reaction, spectators do play some role, but they're not going to be in the oxidation and the reduction, and that's really what matters to us, okay? So we're really going to ignore spectators whenever we can. We're really only caring about the things that cause them. That being said, let's take a look at a reaction together for just a second. So let's look at this reaction between aluminum and copper 2 chloride. In this reaction, aluminum is very clearly oxidized because its number goes up, and copper, because its number goes down, is reduced, right? Now, that's all well and good, it makes sense, but there's this chlorine hanging out here, and for a moment I'm going to ignore this 2 and this 3. That's because if you notice, these -1s don't change. These numbers down here are allowed to change. They're just making things what's called electrically neutral. They're just making it so the Al and the Cl minus, Al plus and the Cl minus, they cancel out, right? It makes it so the charges over here are a net 0. So we're only interested in the green numbers, in the oxidation state. And chlorine, unlike, let's say, aluminum that went from 0 to 3, chlorine didn't change at all, right? And because chlorine doesn't change, it doesn't participate in the oxidation reduction in quite the same way that, let's say, the aluminum or the copper do. So what we can do here is we can ignore this. And this is really the reaction between aluminum and the copper plus 2 ion to make the aluminum plus 3 ion and copper as a metal. The chlorine, it's in the reaction, but it's a spectator. And for the rest of the time, if it's a spectator, we get to ignore it. So a formal definition of a spectator is things that are neither oxidized nor reduced. They just kind of watch the reaction, right? So let's do a quick check-in. In this reaction, which thing is the spectator? I want to be really clear that it's a spectator because these numbers don't change. I'm not interested in the subscripts. Again, these numbers down at the bottom don't matter to me right now. I'm just looking at the oxidation state, the green number here. And if that number doesn't change, that's the spectator. While we're here, it'd be good to quickly say, hey, which one was reduced? So let's do another quick check-in. Which of these chemicals was undergoing reduction? So the iron went from 3 to 0, which is a reduction reaction, right? Because the green number fell. And this would be a much more common situation in chemistry, where we have all of these different possibilities. The reduction, oxidation, and spectator. And like this reaction we see a lot. It's the thermite reaction. I like to come back to it because it's very easy to understand and you've seen it in real life. And so this is normally going to be our first step, is doing exactly what we've been doing, identifying the oxidation, the reduction, and the spectator. Because it's so important, I want you to do it again. Really quickly, in this reaction, which thing is being oxidized? So the oxidation happens between zinc and the zinc plus 2 state, right? This number went up. And where's the spectator here? And notice this is the spectator because these numbers don't change. Again, I know this number down here changed. That's allowed. All I'm looking at is the oxidation states. And because this went from -1 to -1, because it didn't change, that makes this the spectator. Of course, hydrogen in this case is being reduced. All right, so let's get into the meat of it. How do you actually write a half reaction? That's the game we're going to play. And I'm not going to define half reactions. I think it's easier just to see them and be like, oh, well, that makes some sense. So let's look at a half reaction. We're going to identify the oxidation reduction as a first step. So that's pretty easy. So let's look at this reaction between calcium and oxygen to make calcium oxide. And instead of doing this with Edpuzzle, let's just quickly work it through together. So let's connect the calcium to the calcium, and the oxygen to the oxygen. Great. So right off the bat, I already know there's no spectators because everything's got a partner that changes, right? Calcium goes from 0 to +2. The number goes up, so we call that oxidation. And specifically to go from 0 to +2, it did what? It lost 2 electrons, right? And that's actually going to matter a lot for this. And here, oxygen goes down. It's our reduction. And of course, in this case, it's going to gain electrons. It's going to gain 2 of them in this case. All right, so there's our reaction. And pretty straightforward. The question we're about to ask, let me kind of arrange these things pretty carefully here. The question we're about to ask is, how did the reactant become the product? What changed between, let's say, this calcium and this calcium? Well, what we're going to do is we're going to split these into 2 different half reactions. One half will be the reduction half, and the other will be the oxidation half, right? So one half will deal with calcium, and one half will deal with oxygen. As we can, let's start off with calcium, and that's our oxidation. So we need to write an oxidation reaction, right? So let's see, let's think this through quickly. Calcium became calcium, but in the 2+ state. Okay, that's really weird. If I look, I went from calcium to the calcium ion, right? I went from the metal to the ion. So what I'm doing is I'm writing the element, and then I'm writing its charge here. And then I'm going to say, how did that happen? Well, calcium went from the Ca2+ because it had to drop its 2 electrons. So we're actually going to write the electrons into the equation. The fact that this is actually happening is part of the equation. The electrons become a product. In this reaction, calcium gives up electrons. But those electrons didn't just go away. They exist. They're real things. Something took them, right? Something gains electrons, or something's losing them. And of course, that's what a reduction is. So the reduction in this one's a little harder. But before we get there, maybe it quickly would be wise to make sure you understand what's going on. So a quick question. All right, so we've got this. And we need its partner. You just told me that was going to be oxygen, right? And oxygen is going to change to the 2- state. So we need to write a reduction reaction here. But the question is, how does oxygen become O2-, right? How does that actually happen? Oopsies. Kind of line these up for you for a second. Well, I can't add plus charges here because plus charges aren't allowed to be played with in this chapter, right? We have to work with minuses. So the only way for a 2- to end up on this side of the equation is for it to pick up a 2 minus over here, right? Being clear again, this 2 minus, if you missed that last question, is coming from the fact that this 2 minus exists here, right? We're taking the element and slapping the charge on it. So each atom of oxygen is picking up 2 minus charges. Now this is still a little confusing, I get it. But together I think you can see these two things work. The calcium ends up giving away its electrons, and the oxygen ends up taking them. Now, a confusing thing to a lot of people is this 2 here. And technically, this isn't the complete reduction reaction just yet. But for our class, I'm much more concerned about you being able to identify the species, that is the atom, and what's happening to each atom, rather than try to balance all this stuff up. Right now, each time this happens, each atom of oxygen is losing 2 electrons. I think that's good enough for us to really understand. It's been about 10 minutes, so it'd be good to take a quick break. This is calcium metal being burned, and Chemical Force, a YouTube chemist here, is going to pour liquid oxygen on the burning calcium metal. As you can see, it's a really energetic reaction. That's because liquid oxygen is a very pure form of oxygen, and it burns quite well. That's real time there. You can see how quickly this reaction actually happens. And one thing that stands out to me is how hot this reaction is. As he's doing these, I want you to notice how absolutely bright white the inside of this crucible gets. You know this thing is burning incredibly warm. Not something I could easily carry out at Rockhurst, but it's neat to see it this way. I've never seen this reaction actually carried out, so I really appreciated seeing it. And actually, this whole video has a ton of different metals reacting with liquid oxygen. It's pretty neat to actually see if you want to find it yourself on YouTube. Just Chemical Force and liquid oxygen and metals. This is strontium, kind of not as exciting as calcium. Anyway, back over to our lecture. Alright, so let's slowly go through another reaction here. We have the reaction of zinc and hydrochloric acid to make zinc chloride and hydrogen gas. This is what you use to power your 2-liter bottle rockets when we had those, right? So the first thing we need to do is we need to diagnose this reaction and figure out which species is being oxidized, reduced, and a spectator. So I'm going to draw lines here really fast for you. And I'm going to ask you a series of 3 quick Edpuzzle questions, asking you to make sure you really are good at this step, because this step is frankly the hardest step. Alright, so you've identified that zinc is being oxidized, or that this is oxidation. How about this red line? And what's the name for this chlorine? It doesn't change the charge again, so what's the name for that when that happens? Alright, so we've got 3 different parts of this reaction. We have an oxidation reaction, we have a reduction reaction, and we have a spectator. So right off the bat, another question. Which one of these are we going to ignore? Alright, so we're going to ignore the chlorine, and that means we need to write an oxidation reaction for zinc, and a reduction reaction for hydrogen. So let's start with the oxidation, and what we're going to do is I kind of want to just scratch down what happens. Let's see. My zinc, in its not charged state, right, becomes zinc in the 2 plus state, right? Zinc goes from 0 to 2 plus. So the question I have to ask is, how does a 0 become a 2 plus? I'm not allowed to play with pluses. I'm only allowed to play with minuses. So I can't write a plus 2 over here, right? I can't add protons. So this side of the equation, there's nothing I can do to make this side of the equation make sense, right? It's got to stay the same. Okay, so far I'm going to have zinc turn into something. And it's got to turn into zinc 2 plus because we already know that. But that's not balanced. The plus 2 had to come from somewhere. So how many electrons does zinc need to lose to become 2 plus? So as you just said, to get 2 plus, you have to lose 2 minuses, right? You've got a minus 2. So I'm going to say that this happens because it loses the 2 electrons. So let's look at the reduction side of things there. Again, I'm just going to sketch out what I see happening. I see H in the plus 1 state becoming H in the zero state. Kind of something like that, right? Now, I'm not allowed to add pluses, so I can't just go like H plus 1. I really need to get rid of the plus. If you want to think about it, in some ways, generally the electrons are going to end up with the thing that's got the charge, generally. So I need to take that plus, right? And I need to turn it into something that is 0, H alone. So how many minuses, how many electrons does this H plus need to become 0? Quick question again. Now, you might notice that the electrons aren't equal in this reaction. And that's okay for now. Again, I'm much more concerned about what's happening at the atom level than the reaction level. And if you really wanted to explain how that happens, well, there's this 2 up here that's helping explain that, right? I could, and I don't need you to do this just yet, I could go as simple as something like this. And that would work. But for now, that's not necessary. All right, let's take a look at a video of this reaction because it is a neat one. So you've seen this reaction in real life, but here they're just adding hydrochloric acid at about a 35% concentration to zinc, and just the balloons filling up with hydrogen. It takes a while, so let's speed it up here. And ultimately you get these lovely balloons full of hydrogen which float, and they're used throughout the world, which leads to this viral video from a while ago.
Happy birthday to you!
Oops. And I'm really glad that everyone in this case is okay.
Oh my god!
That was very stupid.
And especially that guy does such a good job about taking it. Alright, so let's look at one more reaction. One more reaction we actually looked at the beginning of this video, which is between a metal and copper 2 chloride. And I've drawn 3 lines here. And my first question is, which of these is a spectator? Great. Now how about this one? Which one's being reduced? Which leaves behind the oxidation, which is of course the zinc, because it goes up to +2. So we have those 3 things, and like magic they're going to appear. So we've got an oxidation reaction, here the zinc in orange, and a reduction in red of copper. So again, the first thing I want to do is before I write anything else out, I want to figure out what's going on. What happens in the zinc? Okay, so for the oxidation reaction, it goes from zinc in the 0 state to zinc in the +2 state, right? Zinc in 0 to zinc +2. Great. So zinc in the 0 goes to zinc +2. So for reduction, I want you to pick from the list which of the things you think is going to happen. Great. So we have the copper +2 going to copper 0. So those are our 2 reactions. Let's take a look at these more formally. Okay. As you know, I'm not allowed to add pluses. So I can't say like Zn plus 2 protons, right? I can't do that. The only thing I can do is I can cancel out the plus charges with minus. So if I have zinc and it turns to zinc +2, then I need 2 electrons to cancel out that +2, right? So I can't just add 1, but I need to add 2 individual electrons. And again, the reason why this 2 is here is because to get from 0 to +2, I had to lose 2 electrons. In other words, zinc needs to give up 2 electrons and turn into its ion. Okay. Over here on the reduction side, obviously, I need to turn into copper, and my minuses need to cancel out this plus, right? So how many minuses do I need? All right, so we're going to show those 2 minuses as 2 electrons by just writing them in as 2 electrons. At this point, we're getting pretty good at writing half reactions. So here's our overall reaction, and here's our oxidation and our reduction reactions. Now, technically, these little bits here aren't needed, right? The actual half reaction is, apologies, the world's shifting, is just this part here. The actual reaction is just this part here. This part here only helps us write them, in other words. I'd like to take a look at this reaction in real life. Here's a time lapse in just a second to close this video. But that's all you need to do in terms of learning half reactions. The next things to do will be to actually practice it. I thought about doing a couple demonstrations as part of this, a couple like hands-on experiments here. And I think I'm going to actually do that in the next video. This video is already pretty long as it is, and I think adding another 10 or 15 minutes of reactions here is just not worth your time today. So, until I see you next time, buen camino en todo.